Okay, we are back in part 3. We are going to talk about the solar cell. What we try to do in this series, we like to simulate the solar cell using the electrical circuit knowledge we have from your either physics course or electrical engineering course. And what our objective in this section is to find out the power comes out of a solar cell when you have given light impinging upon it. So that's what we are trying to find out. So what we do is we start with what's called a PN junction diode, and this is very commonly known knowledge in physics or in the first course in electrical engineering. So here what we do is we represent the PN junction. This is the red color is the P material, N is the N type material, and then we apply the voltage across it. When you do the apply the voltage, then we are going to have the current flowing through it, and this can be modeled as a diode. So this essentially ID, which is the given by the diode current in amperes, and the direction of the arrow shows which way the current is flowing across the terminals, that is from P side to the N side, and then I0, which is given as the saturation current. So when you trying to reverse it, the current will not flow through this. So the current, the diode, purpose of the diode is simply to allow the current to flow in this particular figure from the top to the bottom. And the typical diode equation is given like here, which you have seen it before. The current flowing through the diode is equal to what is called the saturation current, and multiply by the exponential to the power of q, which in this particular case q is the electron charge, which is given here. Let me see. So which is the value of which is given in this particular case here. This is the value for the charge, and the K is the Boltzmann constant, and the T is the junction temperature. And it is important to note that the temperature of the diode plays a significant role, and similarly on the solar cell a significant role. So it will come again and again, the effect of the temperature we will talk about later. So this is the simple diode equation, and since most of them are constants, so this boils down to the constant value and multiply by the voltage across the diode divided by the temperature. At 25 degrees C, for example, and you can simply rewrite this equation here as u to the power of this constant multiplied by Vd minus 1. So if a given operating temperature, you can see the diode equation simply written as in this fashion. When, for example, when the battery, when you are connecting in this fashion, where the positive of the battery is connected to the P material, negative battery is connected to the N material, then the current is going to flow, and this particular thing is called the forward bias. And if you reverse these connections here, of course very little current is going to flow. That is actually what the I naught is in this particular curve. So what we are plotting here is the current versus the voltage, and as you can see, when you reverse it, then very little current is flowing through this, and that is called the reverse current of the little bit of it there, but that is very little. And so this is typically will give you the diode current voltage curve. So only when you are applying, when increasing the voltage here, then the current start going up in this fashion almost exponentially. So the simplified equivalent circuit. So what we do is we simplify the circuit for the solar cell. In this particular case, this is your PN junction here, and schematically what we are showing is the sun's radiation is hitting, or the photons are hitting the solar cell, and we have the load shown on the other side, and then the current will start flowing into the load. So imagine that you have an electricity bulb hooked to this. So from the PN junction, as the sun is shining on the PV junction, current will flow, and then you will have the electricity, and you can light up a bulb, for example. So the illuminant light causes the current to flow in the load, and this circuit can be equivalently written as like this, and this is the what is called the short circuit current associated with the p-n junction, and this is the diode current which is flowing through, and there is a load. So, essentially same thing is represented. Equivalent circuit for this is going to be this one. Then we can analyze this by using the simple Kirchhoff laws. So, the current flowing through the entire circuit, which is I, is given as the ISC, which is a short circuit current, and minus the diode current. And we already know the expression previously from the diode current. So, you substitute it for this one, then you get the essentially the current I is equal to this particular value. And the ISC, which is essentially is what is called the short circuit current. When there is voltage is equal to 0, then current will become the ISC, which is a short circuit current. And then you have the open circuit, then you have what's called open circuit voltage, then the current becomes 0, then you can V open circuit becomes V sub D, and this is equal to 0, then you can solve for the V sub D in that particular case, which is equal to V sub O. So, let me see whether I can write that. So, in this case, so you are essentially you are solving for this, and this is equal to simply V sub D at I equal to 0. So, that is what this equation is. So, this is very important. This is the open circuit voltage, and that is the short circuit current, and these two plays a very important role in the solar cell. So, then if you plot that, for example, in this case, so what we are doing is we are plotting voltage versus the current. So, the voltage is equal to 0, then we have short circuit current, and then as you increase the voltage, or you increasing essentially when the light is shining on it, and this is what the curve is followed until when the current is equal to 0 in this particular case. So, this is simply this ISC is directly proportional to solar insolation. The brighter it is, the more electrons, the intensity of the light will determine the number of electrons released. So, the brighter it is, the higher the ISC is going to be. Then of course, the frequency is going to play a role. That gives you the more higher the frequency, the more energy is going to come. So, in this particular case, the important factor is the light intensity of the light, and that is shown here. This is for a typical cell. This is a typical solar cell in reality, and this is the current. And when you are apply the full sun in this particular case, meaning I think we can still write it. Full sun meaning roughly around 1000 watts per meter square. That is what we mean by full sun. When you apply that for a typical cell, you get about 4 amps in this particular case, and eventually the open circuit voltage is typically around 0.6 or so. So, what you get is about 2.4 watts are what you are going to get from a typical cell when you have the full sun shining on it. Now, if the intensity of the sun goes down, and then of course, let us say half sun, that is only 500 watts per meter square, then of course, the curve is going to come down, and the power curve is going to look like that. And you can see there is not a significant difference in the open circuit voltage when the intensity of the light is varied. So, the intensity of light has a significant effect on the current, not much effect on the voltage. So, this is not going to change very much, but when the wattage is changing, and that change is primarily due to the change in the current, and that is what the IV curve is going to look like. Now, of course, in reality what is going to happen is you are going to have connections associated with the cell. So, because you have to connect these leads to the load, for example, then you are going to have some resistance associated with this, and this is called leakage resistance. So, simply we keep adding things to the circuit, and this is the load here, and then we analyze this, what happens when you have the additional resistance in the circuit. So, this is the solar cell in this particular case, like before, p-n junction, and this is the diode and then this is the additional resistance. This, for example, is in the parallel resistance, and we can also apply the serial resistance to the circuit. And you can do combination of the both. Typically what we do is eventually when you do the total simulation of the solar cell, we don't have the parallel resistance and serial resistance added to it. So when you do that, it's called parallel leakage resistance. Then the current is going to be less because this is what we had before, and minus because of the resistance you are going to have this quantity right here. So it is going to be decreased by the voltage divided by the resistance of the parallel resistance which you have included in the circuit. And similarly, when you are doing the series resistance in this particular case, then the current of course is going to be given by this value as before, and Vd in this particular case is going to be replaced by this value right here. So this is the, when you have the serial resistance, you have for Vd is replaced by this value. When you have the parallel resistance, of course you have this parameter comes under the equation. So now what we can do is, because in a real solar cell we have both the serial resistance and the parallel resistance included. So we will put both of them together, and that's what we are we did here. So we have both the serial and parallel resistances, and we can redo the Kirchhoff law. So this is applying the Kirchhoff law to the real solar cell, and we get this particular equation here. This is the short circuit current, is the current flowing through the circuit, going through the diode and going through the resistance here. When you do this for a parallel resistance, you get the IV curve is going to look something like this. So this of course cannot be solved directly. So we have to do a iterative procedure. So we assume a value for V sub d, and then we calculate I, and then we plot this I versus V curve what we have shown before. The voltage across an individual cell can then be found out by this equation right here. So this is essentially the current for the real cell. Oops, let me see. So the current is given by this equation here, and the voltage is given by this equation right here. So the series resistance affects the voltage, and the parallel resistance will affect the current, and that is how the solar cell, real solar cell, is modeled using these resistances. And if you plot that now, this is the effect of the resistance. This is the Rp, is very high Rp in this particular case. Let me see here. So serial resistance is 0 in this particular case, and we have the parallel resistance. So you can see when you have the ideal cell is something like this. This is the without any resistance here. When you apply the resistance, and then you can see the curve is going to go down. Now one of the things you have to remember here is the area under the curve will give you the power. So simply when you have this kind of a behavior, when you apply the resistance, the area under the curve is going to be reduced by that much amount, and the power is going to go down. And in this plot here, we have same thing in this case, and then we have applying the series resistance in this. So this is, I think this is the series resistance in this particular case. So the total, the effect of the resistance is reduce the area to the maximum power. So the current is given by now in this particular expression, where you get this due to the series resistance, and the voltage is also given by this function. So you put both the series resistance here and the parallel resistance here, and this is the typical solar cell. That is how it's simulated, and the current is given by this expression right here. So when you plot it, and it's going to look something the real solar cell will have a behavior something like this. And this is the solar cell. So essentially this is the area the light is shining on, and then we get the current across it and that is modeled by this expression right here. So, this is simple, this is easier way to simulate a solar cell and obtain this curve, and if you do the experiment and you take a real solar cell and plot the data, it is not too far removed from the behavior seen in this picture. So, then we have to few definitions we have to use when you look at any technical specification sheet of any solar cell, and what you find out from there is the values given for the open circuit voltage, and then they give you the short circuit current. So, that is how when you buy a solar cell, these comes with as a specification for the solar cell. So, the current, of course, in this particular case, you can similar what we have just done is do this analysis of this circuit. So, these two are important, and this is what is given for that, and typically they also give you the temperature at which the cell is operating and the insulation or the radiation applied to the cell. So, when you plot this curve, which is the I versus V, which we just seen it. So, this is the ISC, we start here, and then you have the current which comes here, and this is the VOC. So, this is the typical curve which you will see. In this curve, what we see, what we define, what is called the maximum power point, and so this maximum power point is given somewhere here, that is where you get the max. So, if you plot the power, which is the multiplication of I times V, as you can see when the V is 0, you start out something like this. So, this essentially represents the area under the curve. So, it's continue to grow, and then it peaks at some point and start coming down, and this peak, which is at the peak in the power point, it corresponds to the IV curve this point. This is called the maximum power point, and this plays a very important role in the solar cells, because we like to operate always at the maximum power point condition. So, in fact, when you are connecting the modules and with the intensity of the light is changing, it is always trying to operate at this condition at the maximum power point. And so, then we define what is called the fill factor, and fill factor is defined by this definition here, which is very important, and this is essentially this is the current density and times by the voltage at the maximum power point. So, this is the maximum power point voltage and the maximum power point current here. So, the fill factor is essentially given by the area under this curve, which is the dotted line which you see. This is the area under the dotted line curve divided by the area under this particular thing right here. So, this is the open circuit current density, short circuit current density and open circuit voltage, and this is a very important one definition, because when you are trying to define efficiency, we use the fill factor. So, the fill factor is simply the area under the rectangle and divided by the area under for example, if you take this is the area. So, this rectangle area divided by this rectangle area will give you what is called the fill factor, and that is very important, because when you define the efficiency of the cell, and this simply says the power density delivered at the operating point. So, in this particular case, this is at the power obtained at the maximum power point, and that is what is delivered, and this is the incident power density. So, this is essentially how many watts per meter square we are applying to the cell, which is essentially sun's radiation, and this is what we are getting out of it at the maximum power point. And this we can write in terms of, because for a given cell the technical specification will give you these two quantities, and they also give you what is called the fill factor. So, when you know these quantities, and then you can the input to the cell is this, and divide this one by this will give you the efficiency. So, when you plot that, this is gives you the short circuit current in this particular case, and this is the open circuit voltage, and the theoretical limit for this is about this. In the theoretical curve is given by this square right here, and the silicon you can get maximum in the crystalline silicon is about 40%, and amorphous silicon and other polysilicon is somewhere right here. These are the theoretical These are the practical things which people have obtained in a cell. This is not for a module now. These are the cell efficiencies in the laboratory conditions. So if you can see on the real cell, for example, you get the efficiencies for a cell is anywhere between 15 to 25%. So crystalline silicon on a real cell, open circuit voltage is about 0.706 and density is about 42 milliamps per centimeter square, and this is the fill factor. So all knowing these things, and you get efficiency of 24%. This is on a typical cell level. Then we have crystalline gallium arsenide here, and that has a little bit higher efficiency, and this is called polysilicon, and this is called amorphous silicon, which people use this to make the thin film solar cells, and this is the CIGS and cadmium telluride, and these three are what is called the thin film solar cells or second generation solar cells. So the maximum you can get is typically efficiency is max, typically you can get is roughly 25% in a crystalline silicon solar cell. So that's what previously in the very beginning I told you, sun power solar cell is pretty close to this value for their solar cell. Almost I think they're reaching about 24% or so for the sun power. So sun power is a company, and they make the most efficient solar cells. So essentially what we have done in this section is we talked about the IV curve for a solar cell, and then how that changes with the intensity of the radiation, and then we defined important quantities of the open circuit current density, short circuit, excuse me, this is the short circuit. So this OC, in fact this is J sub SC, you have to write, and that is V sub OC. So this is, there is a mistake here, this is the J sub short circuit current. So we defined these quantities, open circuit voltage and short circuit current, and then we define how to get the efficiency of the solar cell. Now what we have, this is pretty much in the ideal conditions. So we are only getting the efficiency of about 25%. Now you ask yourself, where is the other 75% of the energy is going? So those are the losses in the solar cell, and we want to minimize them, and we will look into how to either improve on this efficiency or minimize the losses for a particular material. That is what we will address in the next section. Thank you.